All right, so I want to take a moment to derive the equation for centripetal acceleration. So as I mentioned in our circular motion discussion video, I said that if you would like to see where it came from, you can pop over and watch another video. Now, this derivation works a little bit better if we were able to use some calculus, but that's all right. We have a way to get through it with our algebra-based AP Physics 1 skills. So I want to look at an object that travels from this first position around the circle to the second position. So I've already drawn our linear velocities, which are the ones that are tangent to the circle, which are the ones that end up being in our equation for our centripetal acceleration. And these two spots are at identical spots on the, or these two positions are at identical spots around the circle. So one is on this side, come around to the other side, but they're at the same position over here at the top of the circle, okay? So this initial velocity is going to have a component that is in the x direction, and I'm just keeping like classical horizontal being x, and then a component in the y, so classic vertical being y, okay? Now, I'm going to label this theta here. All right, so that's the one we're going to use in our little derivation. So then our final velocity would also have a component that is in the x, and it would have a component in the y. And then this angle right here, this theta should be the same theta if they're at the same spot on the circle from one side to the other, okay? So if I look at the change in velocity, okay, and I'm going to look at the change in the velocity in the x, you can see that both of those velocities in the x are pointed in the same direction, okay? They are at the same angle to the hypotenuse, and we're in uniform circular motion, meaning that I am not speeding up or slowing down. The only acceleration I have is our centripetal acceleration that is causing direction to change. So if all of those things are the same, then, and I looked at v final x minus v initial x, those two values should be the same. So the change in velocity in the x should be 0. So for this particular example, I'm going to look at that centripetal acceleration being the one that caused this y component to move up to down, okay? So it's not always just the y, but for this specific derivation, I've picked 2 points where it would only be in the y. So then I'm going to look at my change in velocity in the y. So I'm going to say that that is negative v final y, making it negative because it's pointed down, minus our v initial y, which was pointed upward. So those are these blue lines, okay? Now, if everything for the x's were the same, right, then everything for the y's are also the same, except for I have this nice negative here. So that ends up making them subtract each other here and become a negative 2 vy. Okay, so I've dropped the final and dropped the initial because they have the same magnitude. And I'm just going to say that now I have negative 2 of that value. The y components in both of these triangles, the blue, are opposite to the theta. And when they're opposite to the theta, then I'm going to use the sine function. So delta y would then be equal to negative 2 v sine theta. All right. And I want to think about, oh, I didn't mean to put delta y. Right, this was delta Vy. All right, so then I'm doing the change in velocity because I'm going to go back to the idea that acceleration is the change in velocity over time. So that makes my acceleration equal to negative 2 v sine theta over t. Okay, I'm going to eliminate that t because we already know that our equation for this acceleration that we're trying to describe is v squared over r, so there's no t in sight. So I'm going to think about our velocity, or really our speed. Remember, our speed is constant here. I'm going to look at that being a distance over time. So if I come back up here to try to describe the distance it travels, okay, I'm going to chunk this or split this circle in half, okay? So I'm going to call this distance from here to there arc length S, which is going to make this distance from there to there also arc length S. But if it does the whole thing from here to there, it would cover a distance of 2S, okay? So I'm going to make this 2s over t, okay, where s, our arc length, is equal to r theta. So that makes this velocity equal to 2r theta over t. And if I rearrange this for t, because that's what I'm trying to eliminate from my equation, then t would be equal to 2r theta over v. So I'm going to come back over here and I'm going to replace t with that value. So our acceleration is then equal to negative 2 times v sine theta divided by our 2r theta over v. And when I divide by a fraction, I can multiply by the reciprocal. So that's going to make this negative 2 v squared sine theta divided by 2r theta, okay? Now I can cancel out some things. So I'm going to get rid of these 2's, okay? And I'm also going to get rid of this negative because that negative is a directionality bit that only applies to my specific from here to there. But I'm trying to come up with an equation that could work from here to there, or there to there, or there to there, or there to there. So any spot around the circle. So I'm just going to drop that negative because that is the piece here that's specific to just the one part that I'm looking at for this derivation. So that leaves me with acceleration being equal to v squared sine theta over r theta, okay? Now, for this last bit, we have to use something that's called the small angle approximation. All right, and the small angle approximation means that at small angles, the sine of an angle is basically equal to the angle. So an example would be that sine of 0.1 is equal to 0.998, which is basically 0.1, okay? So for any of these pieces, we're going to be looking at these small angles. So I'm going to use a small angle approximation here to say that the sine of theta is basically theta, which would allow me to get rid of this sine theta and get rid of this theta. They would cancel out if they are the same thing. So then I'm left with this acceleration, which is our centripetal acceleration, being equal to v squared over r. So as promised, there is our derivation here to get this equation of v squared over r. Let me know if you have any questions.